That faint streak across our night sky hides an incredible secret. You're looking at your own cosmic home from the inside. For thousands of years, humans had no clue what that pale band was. Ancient Greeks called it Galaxias, the Milky Circle. They thought it was glowing mist. Galileo's telescope changed everything. What looked like smooth fog turned out to be individual stars, billions of them, each one a nuclear furnace burning across impossible distances. We'd been staring at a massive stellar city while thinking it was empty space. This view from inside explains what we see perfectly. We sit within a flat disk packed with stars. When we look along the disk's edge, we see layer after layer of distant suns. They blur together into that ghostly glow. When we look up or down from the disk, we see far fewer stars and can peer into deep space. The evidence surrounds us every clear night. We live inside the very galaxy we're observing. Our solar system lives in the cosmic equivalent of a quiet suburb. This location probably saved our existence. The galaxy's center is absolutely terrifying. Stars packed together thousands of times more tightly than in our neighborhood. Massive stars explode regularly as supernovas. Deadly radiation floods everything. A monster black hole lurks at the core, heavier than millions of suns combined. We avoided all of this chaos by living far away. Dense cosmic dust clouds blocked astronomers from figuring out our exact location for centuries. They couldn't see through the galactic haze to map where we actually sit. Modern telescopes finally cracked the mystery. We live in a minor spiral arm that astronomers call a spur, basically a small branch connecting two major galactic highways. This safe distance isn't just luck. We're close enough to the action to benefit from heavy elements that dying stars created over billions of years. These elements built our rocky planet and our bodies. But we're far enough away to avoid getting fried by stellar explosions and radiation storms. We found the perfect spot for life to survive and thrive. Right now, you're moving through space faster than you can possibly imagine. You'll never feel it. Our entire solar system races around the galaxy's center like a horse on a cosmic carousel. This carousel has been spinning since the universe began. Most people live their entire lives without realizing they're passengers on this ride. The ride stretches across distances that make human comprehension break down. Stars closer to the Galactic Center zip around at incredible speeds. Out here in our cosmic suburb, we cruise more leisurely. One complete lap around the galaxy takes longer than human civilization has existed. But here's where things get weird. Stars throughout the galaxy maintain nearly identical speeds regardless of how far they are from center. Normal physics says this should be impossible. Outer stars should be crawling compared to inner ones. This reveals something shocking. Our galaxy contains far more invisible matter than visible stars. Scientists call this mysterious stuff dark matter. Without it holding everything together, the outer regions would simply break apart and fly away into space. We're all passengers on a carousel made mostly of invisible material. Cosmic dust blocks our view in every direction we look. This material acts like fog, hiding the galaxy's true shape from anyone living inside it. For centuries, astronomers had no idea what kind of galaxy we actually live in. The dust clouds scattered throughout space made it nearly impossible to see the big picture from Earth's position. Advanced infrared telescopes finally pierced through this cosmic fog. What they revealed shocked everyone. Our galaxy isn't just a simple spiral. It contains a massive stellar highway stretching across its center. What astronomers call a central bar. This bar is basically a dense concentration of stars arranged in an elongated shape. We live inside what's called a barred spiral galaxy. The central bar acts like the galaxy's main organizing system. It collects material from the outer regions and funnels everything toward the center through spiral arms. This central feature has been organizing our galaxy's design for billions of years. But dense dust throughout the galactic disk kept this discovery hidden until recently. Sometimes the most important structures are the ones you can't see from where you're standing. Our sun represents cosmic mediocrity at its finest. Among hundreds of billions of stars in our galactic neighborhood, our sun ranks as utterly ordinary. Astronomers sort stars into different categories based on their size, temperature, and brightness. Our sun falls into the category they call main sequence, basically meaning average star that burns fuel steadily. It's the stellar equivalent of a middle-class suburban resident. The galaxy contains far more spectacular neighbors. Red supergent stars grow so massive they could swallow multiple planets from our solar system whole. Blue hypergent stars burn so intensely they blast out thousands of times more light than our sun. Tiny red dwarf stars, the most common type, burn so slowly they'll outlive our sun by trillions of years. Even our sun's eventual death will be completely unremarkable. No dramatic explosion. No spectacular fireworks, just a gradual fade into a dim white dwarf star that slowly cools over billions of years. But this completely ordinary star created the perfect conditions for rocky planets to form and life develop. Sometimes the most average things produce the most extraordinary results. Ancient star clusters hold the key to finding our galaxy's center. These clusters are like cosmic lighthouses pointing the way home. Globular clusters are some of the oldest objects in our galaxy. Each one contains hundreds of thousands of ancient stars packed into a tight ball. These stellar cities formed when the galaxy was young and have been orbiting the Galactic Center ever since. Here's the crucial clue they provide. They're not scattered randomly across the sky. When astronomers mapped where these clusters appear in our night sky, they discovered something remarkable. Most of them cluster heavily in one particular direction, toward the constellation we call Sagittarius. This lopsided distribution tells us exactly where the galaxy's center lies. The globular clusters are all orbiting around the same central point, like planets around a star. From our perspective, we see most of them bunched up in the direction we need to look to see the galactic core. Dense dust clouds block our direct view of the center in visible light. But the globular clusters act like cosmic breadcrumbs, marking the path through space to our galaxy's hidden heart. Without these ancient star clusters, we might never have figured out which direction to look for home. Our solar system doesn't sit exactly in the middle of the galaxy's main disk. We live slightly above it, like residents on the upper floor of a cosmic apartment building. The galaxy's main disk contains most of its stars, gas, and dust all flattened into a relatively thin layer. Think of it like a cosmic pancake with most of the action happening in the middle. But we're positioned a bit north of this central plane. This elevated position gives us some major advantages. The main disk is packed with cosmic dust that blocks light and makes it hard to see distant objects. By living slightly above this dusty layer, we get a clearer view of the universe beyond our galaxy. Our position also reduces our exposure to some of the galaxy's more dangerous neighborhoods. The main disk experiences more stellar explosions, radiation, and cosmic chaos. Our slightly elevated address keeps us out of the worst of it. Astronomers can detect this vertical offset by studying how the Milky Way appears in our sky. The galactic band doesn't run exactly along our celestial equator. It's tilted relative to our position. This cosmic elevation might seem small, but it makes a huge difference in what we can observe and how safe our neighborhood remains. For most of human history, we had no clue where we actually lived in the galaxy. Finding our cosmic address required revolutionary new tools and decades of painstaking measurement. The key breakthrough came from special stars called Cepheid variables. These stars pulse like cosmic lighthouses, getting brighter and dimmer in a regular cycle. The amazing thing about Cepheids is that their pulsing period tells you exactly how bright they really are. This makes them perfect cosmic measuring sticks. By comparing how bright a Cepheid appears to how bright it should be, astronomers can calculate exactly how far away it sits. It's like determining distance by comparing a light bulb's apparent brightness to its known wattage. Scientists use this technique along with other distance indicators to map our position with incredible precision. They combined measurements from space telescopes, radio telescopes, and ground-based observatories to triangulate our exact location. The final answer shocked everyone with its precision. We sit roughly 26,000 light-years from the Galactic Center, about halfway out toward the galaxy's edge. These revolutionary measurement techniques transformed us from cosmic wanderers with no address into residents with a precise galactic zip code. Our sun doesn't live alone in space. It's part of a local stellar community, like a cosmic neighborhood where all the residents share similar backgrounds. When astronomers studied the stars near our solar system, they discovered something fascinating. Many of our stellar neighbors have remarkably similar ages and chemical compositions. It's as if they all came from the same cosmic family. This similarity isn't coincidence. Stars form in groups when giant gas clouds collapse and fragment into multiple stellar nurseries. The stars that form together start with similar raw materials and roughly the same age. Over millions of years, gravitational interactions gradually scatter these stellar siblings across the galaxy. Our local stellar group represents the scattered descendants of one of these ancient star-forming regions. Though the original stellar nursery dissolved long ago, we can still identify our cosmic relatives by their shared chemical fingerprints. These stellar neighbors move through space together in roughly the same direction at similar speeds. We're all part of the same galactic traffic pattern, flowing around the galaxy's center like cars on a cosmic highway. Understanding our local stellar family helps astronomers trace the history of star formation in our corner of the galaxy. We're not just random travelers. We're part of a community with shared origins stretching back billions of years. The direction toward our galaxy's heart remained hidden behind an impenetrable cosmic fog for most of human history. Dense dust clouds block our view like a thick curtain drawn across space. When we look toward the constellation Sagittarius, where the galactic center lies, we see almost nothing in visible light. Countless tiny dust particles floating between the stars absorb and scatter the light from distant objects. It's like trying to see through a sandstorm that stretches for thousands of light years. This cosmic dust problem frustrated astronomers for centuries. They knew the galactic center had to be somewhere, but couldn't penetrate the obscuring veil to actually see it. The breakthrough came when scientists learned to use different types of light. Infrared light passes through dust much more easily than visible light. Radio waves travel through dust clouds like they're barely there. Modern infrared and radio telescopes finally pierced the cosmic fog. They revealed the Galactic Center in all its violent glory, a chaotic region packed with massive stars, dense gas clouds, and a supermassive black hole. But even today, most of the Galactic Center remains hidden from our direct view. We can study it with special tools, but we'll never see it the way we see other parts of the night sky. The dust curtain will always be there, reminding us that some cosmic secrets stay partially hidden no matter how hard we try to uncover them. Every star in our cosmic neighborhood moves in the same direction around the galaxy's center. This coordinated motion proves we're all part of one enormous rotating system. When astronomers measured the motion of nearby stars, they expected to find chaos. Stars moving in random directions at random speeds. Instead, they discovered something remarkable. All the stars participate in the same galactic rotation. It's like discovering that every car in your city is traveling on the same giant circular highway, even though most drivers don't realize it. The stars near our sun are all flowing in the same direction through space, carried along by the galaxy's rotation. This collective motion reveals the incredible gravitational force holding our galaxy together. Every star, including our sun, is locked into an orbit around the galactic center by the combined gravity of hundreds of billions of other stars plus vast amounts of invisible dark matter. The motion is so smooth and coordinated that we never feel it, just like passengers on a smoothly moving train. But make no mistake, we're all passengers on the same cosmic vehicle, racing through space at tremendous speed. This synchronized stellar dance has been going on since our galaxy formed over 13 billion years ago. Every star is both an individual object and part of a vast collective motion that defines our cosmic home. Understanding this collective rotation helped astronomers realize that galaxies aren't just random collections of stars. They're organized, dynamic systems with their own internal structure and motion. Astronomers needed to invent an entirely new coordinate system to pinpoint our exact location in the galaxy. It's like creating a cosmic version of latitude and longitude. On Earth, we use familiar coordinates. Latitude tells you how far north or south you are. Longitude tells you how far east or west. But these Earth-based coordinates become useless when you're trying to map positions across an entire galaxy. Scientists created what they call the Galactic Coordinate System. This system puts the galaxy's center at the cosmic equivalent of the North Pole. Galactic longitude measures how far around the galaxy you are from a reference direction. Galactic latitude measures how far above or below the main galactic disk you sit. Using this system, astronomers can now state our precise cosmic address with scientific precision. We sit at specific galactic coordinates that place us definitively within the galaxy's structure. This coordinate system also helps astronomers map the positions of other objects throughout the galaxy. Gas clouds, star clusters, nebulae, and other galaxies all get their own galactic coordinates. Before this system existed, describing positions in the galaxy was like trying to give directions without street addresses. Now we have a standardized way to navigate our cosmic neighborhood and communicate precise locations to astronomers anywhere on Earth. Our solar system finally has an official galactic address that will never change, no matter how far we travel through space. A revolutionary space mission called Gaia transformed our understanding of our cosmic neighborhood by creating the most detailed 3D map of nearby stars ever made. The Gaia spacecraft launched with one primary mission: measure the precise positions and motions of over 1 billion stars in our galaxy. It sounds simple, but the technical challenges were staggering. Gaia had to measure stellar positions with incredible precision from space. We're talking about detecting changes as small as the width of a human hair viewed from 1,000 miles away. The results completely revolutionized astronomy. For the first time, we could see our stellar neighborhood in 3 dimensions. Instead of just knowing that certain stars appeared bright or dim in our sky, we now knew exactly how far away each one sits and which direction it's moving through space. Gaia revealed the complex structure around our solar system, streams of stars moving together, clusters that had been invisible before, the detailed shape of nearby spiral arms, even the subtle wobbles that reveal hidden planets orbiting distant stars. This 3D map showed us that our local cosmic environment is far more complex and dynamic than anyone had imagined. Stars aren't just scattered randomly through space. They form intricate patterns and structures that tell the story of how our corner of the galaxy evolved over billions of years. Thanks to Gaia, we finally know our place in the cosmic city with unprecedented detail and accuracy. Among the hundreds of billions of star systems in our galaxy, our solar system ranks as utterly typical. This ordinariness might be the most important thing about us. From a cosmic perspective, our solar system brings nothing particularly special to the galactic table. Our sun is middle-aged and average-sized. Our planets follow predictable orbits. Our location sits in an unremarkable spiral arm far from the Galactic Center. We represent cosmic mediocrity at its finest. But this ordinariness carries profound implications. If life could develop around such a thoroughly average star in such a thoroughly average location, it suggests that life might not require special circumstances after all. Our cosmic address teaches us something crucial about our place in the universe. We're not at the center of anything important. We're not in a special location. We're not orbiting an unusual star. Yet despite this complete cosmic averageness, our planet became home to an extraordinary diversity of life. Complex chemistry led to biology. Biology led to consciousness. Consciousness led to the ability to study our own cosmic origins. This suggests that the universe might be teeming with life around other ordinary stars in other unremarkable locations throughout the galaxy. Our cosmic insignificance might actually be the key to understanding that we're probably not alone. Sometimes the most important discoveries come from realizing just how ordinary we really are. What if I told you that a monster beyond imagination controls our entire solar system's fate? At the heart of our galaxy lurks something so massive it defies comprehension. A supermassive black hole heavier than 4 million suns combined sits at the Galactic Center like a cosmic anchor. This black hole doesn't just exist, it dominates. Its gravitational field reaches across the entire galaxy, binding hundreds of billions of stars into one coherent structure. Every star, including our sun, orbits around this central monster whether we realize it or not. Think of it like the ultimate cosmic puppet master. The black hole's gravity creates invisible threads that extend throughout the galaxy. These threads keep every star locked in its orbital dance, including our solar system. Without this gravitational anchor, our galaxy would simply fly apart into chaos. Stars would scatter in random directions. The beautiful spiral structure would dissolve. We'd be cosmic wanderers drifting alone through empty space. This central black hole is what makes our galaxy a galaxy. One unified system instead of billions of individual stars going nowhere. Our solar system moves in the slowest race in the universe. One lap around the galaxy takes roughly 200 million years, what astronomers call a galactic year. During each galactic year, incredible changes happen on Earth. Entire species evolve and go extinct. Continents drift across the planet's surface. Mountain ranges rise and erode away. The last time we completed a full orbit, dinosaurs ruled the Earth. Since our solar system formed over 4.5 billion years ago, we've completed roughly 20 galactic laps. Each journey around the galaxy exposed us to different cosmic neighborhoods with varying levels of radiation, stellar activity, and interstellar material. This incredibly slow orbital period means most cosmic changes happen faster than we can complete a single lap. Stars are born and die. Spiral arms shift and reform. The galaxy's structure evolves while we're still making our way around just once. Yet this leisurely pace provides crucial stability. We avoid the violent chaos that would come from racing through the galaxy too quickly. Our slow, steady orbit gives planets time to develop stable climates and potentially support life. Our solar system is built for the cosmic marathon, not the sprint. Galaxies don't spin like solid wheels. They rotate in a way that should be impossible according to basic physics. In our solar system, planets closer to the Sun orbit much faster than planets farther out. Mercury races around its orbit in just 88 days, while distant Neptune takes 165 years. This follows simple physics. Stronger gravity closer to the center creates faster motion. Galaxies break this rule completely. Across much of a galaxy, stars can keep more similar orbital speeds than simple visible matter alone would predict, even as you move farther from the center. This is one of the key patterns astronomers measure in galaxy rotation curves. Normal physics says outer stars should be crawling compared to inner ones. The fact that they're not reveals something shocking about our galaxy's structure. This unexpected rotation pattern was one of the first clues that galaxies contain far more matter than we can see. The visible stars alone don't have enough gravity to create this rotation pattern. Our galaxy spins in a way that suggests most of its mass is completely invisible. Here's what will shock you. Most of the matter controlling our solar system's orbit is completely invisible. Scientists call this mysterious substance dark matter, not because it's literally dark, but because it doesn't emit, absorb, or reflect any light. We can't see it with any telescope ever built. Yet dark matter makes up roughly 85% of all the matter in our galaxy. This invisible material forms a massive halo surrounding the visible galaxy. The dark matter halo extends far beyond the farthest stars we can see. Its gravity dominates the motion of everything in the galaxy, including our solar system. Without dark matter, our galaxy's rotation would be completely different. The outer stars would orbit much more slowly. The spiral arms would wind up and disappear within a few rotations. We're essentially passengers in a cosmic vehicle made mostly of invisible parts. The dark matter provides the structural framework that holds everything together and determines how fast we move through space. The force that guides our solar system's journey through the galaxy is something we can detect but never directly observe. Our solar system travels fast enough to tour the entire galaxy, but not so fast that it escapes into the cosmic void. This balance determines our cosmic fate. Every object in orbit has what's called an escape velocity, the minimum speed needed to break free from gravitational bonds. For our solar system to escape the galaxy entirely, it would need to move roughly twice as fast as it currently does. We're cruising at exactly the right speed to remain galactic residents. This careful balance wasn't guaranteed. If our solar system had formed with slightly more energy, we might have been ejected from the galaxy billions of years ago. We'd be wandering alone through intergalactic space with no stellar neighbors for millions of light years. If we'd formed with too little energy, we might have spiraled inward toward the dangerous Galactic Center, where radiation and stellar chaos would have made life impossible. Instead, we hit the cosmic sweet spot. Our orbital energy keeps us locked in a stable galactic orbit while maintaining a safe distance from both the chaotic center and the empty void beyond. We're traveling at precisely the right speed to remain safe galactic citizens for billions of years to come. Every second, two massive forces battle for control of our solar system's fate. Gravity constantly tries to pull us toward the galactic center. Our orbital motion constantly tries to fling us outward into space. These opposing forces must balance perfectly, or our stable orbit would quickly become chaos. This balance works exactly like a ball on a string. Spin the ball too slowly, and it falls toward the center. Spin it too fast, and the string breaks, sending the ball flying away. Our solar system sits in the cosmic equivalent of perfect string tension. The galaxy's gravity provides exactly the right inward pull to match our outward orbital motion. This creates what physicists call centripetal force balance, the perfect equilibrium between falling inward and flying outward. If this balance shifted even slightly, catastrophe would follow. Too little gravity and we'd spiral outward, eventually leaving the galaxy behind. Too much gravity and we'd spiral inward toward the violent galactic core. This delicate balance has remained stable for over 4 billion years. It's so precise that our orbit has stayed within the same general galactic neighborhood throughout Earth's entire history. The forces governing our cosmic motion are locked in a perfect dance that has protected us for billions of years. Nothing in space travels in a perfect circle forever. Our solar system's orbit gets constantly nudged by gravitational interactions with passing stars and cosmic structures. These perturbations are incredibly tiny compared to the galaxy's main gravitational field. A passing star might alter our orbit by less than the width of Earth's orbit around the Sun. Individual perturbations seem completely insignificant. But over millions and billions of years, tiny nudges add up. Each time another star passes relatively close to our solar system, its gravity gives us a microscopic push. Dense molecular clouds occasionally drift through our neighborhood, creating additional gravitational tugs. Even the galaxy's spiral arms exert subtle influences as we pass through them. These accumulated perturbations gradually change our orbit from a perfect circle into a slightly elliptical path. They also cause our orbital plane to wobble slowly over cosmic time. The amazing thing is that these changes happen so gradually that they don't threaten our stability. Our orbit can handle small modifications without throwing us into danger. Our cosmic path gets constantly fine-tuned by gravitational interactions, but these adjustments happen so slowly they've never endangered Earth's climate or habitability. The galaxy's gravity doesn't pull on our solar system uniformly. Different parts of our solar system experience slightly different gravitational tugs, an effect called tidal forces. These galactic tidal forces work similar to how the Moon creates ocean tides on Earth. The Moon's gravity pulls slightly harder on the side of Earth facing it, creating a bulge. The galaxy's gravity works the same way on our entire solar system. The difference is almost unimaginably small. The gravitational difference between the side of our solar system facing the galactic center and the side facing away amounts to less than 1 part in a trillion. For comparison, this is like the weight difference between a grain of sand and a grain of sand plus a single atom. Yet even this tiny effect has measurable consequences over cosmic time. Galactic tidal forces gradually disturb the orbits of comets in the outer solar system. They can nudge comets from the distant Oort cloud onto paths that eventually bring them into the inner solar system. These tidal effects also create extremely subtle changes in the orbits of the outer planets. The changes are so small they're barely detectable, but they accumulate over millions of years. Even gravity as gentle as galactic tides can reshape cosmic architecture when given enough time. There's a cosmic law that protects our solar system from suddenly veering off course. This law, called conservation of angular momentum, acts like a cosmic insurance policy for orbital stability. Angular momentum is basically the universe's way of measuring spinning and orbiting motion. For our solar system, it represents the combination of how fast we're moving and how far we are from the galactic center. Here's the crucial part. This angular momentum can never just disappear. Unless some external force actively changes our motion, we must maintain the same angular momentum forever. This means if something tried to push us closer to the galactic center, we'd automatically speed up to compensate. If something pushed us farther out, we'd slow down accordingly. Think of it like a cosmic speed governor on our galactic orbit. The universe has built-in rules that prevent dramatic, sudden changes to our path through space. This conservation law explains why our solar system has maintained a stable orbit for over 4 billion years despite countless gravitational interactions with other cosmic objects. The fundamental laws of physics act as guardrails, keeping our cosmic journey predictable and safe. Our galaxy's spiral arms aren't fixed like the arms of a pinwheel. They move through space as waves of density, regions where stars and gas temporarily bunch up before spreading out again. This creates one of the strangest aspects of our galactic journey. The spiral arms rotate at a different speed than the stars do. It's like cosmic traffic moving through a slow-moving construction zone. We periodically pass through these spiral density waves. Each time our solar system enters a spiral arm, we encounter regions with more stars, more gas, and more active star formation. These regions experience more supernovas, more radiation, and more gravitational disturbances. Between spiral arm passages, we travel through quieter regions with less stellar activity and fewer cosmic hazards. These calmer periods might provide crucial breaks that allow planetary systems to develop stable conditions. Scientists estimate we pass through major spiral arms roughly every 100 million years. During Earth's history, these passages may have coincided with periods of increased cosmic radiation that affected climate and evolution. Our solar system's journey includes regular passages through cosmic construction zones, followed by peaceful stretches in galactic suburbs. Against all odds, our solar system occupies one of the galaxy's most stable orbital zones. Computer simulations reveal that most possible orbits in our galaxy eventually become chaotic or dangerous. Many galactic orbits suffer from what astronomers call resonance effects. These happen when an orbit's period matches up with other regular motions in the galaxy, creating destructive interference patterns. We avoided these cosmic traps. Our orbital period doesn't match any major galactic cycles that could destabilize us. We don't get locked into resonances with spiral arm rotations, stellar clustering patterns, or other repeating galactic phenomena. This orbital stability isn't just lucky, it may be essential for life. Chaotic orbits would carry us through rapidly changing cosmic environments. We might experience dramatic variations in radiation exposure, stellar encounters, and interstellar material density. Instead, our stable orbit has kept us in roughly the same type of galactic neighborhood for billions of years. This consistency allowed Earth's climate to remain stable enough for life to evolve and flourish. Our solar system won the cosmic lottery by finding an orbit that stays safe regardless of what chaos erupts elsewhere in the galaxy. Our solar system's orbital plane doesn't stay perfectly fixed in space. Like a spinning top that wobbles as it slows down, our entire orbital plane slowly precesses, or wobbles, over cosmic time. This wobble happens because our galaxy isn't perfectly round. The distribution of matter in the galaxy creates an uneven gravitational field with subtle variations that tug on our orbit in complex ways. The precession is almost impossibly slow. Our orbital plane takes roughly 100 million years to complete one wobble cycle. During this time, the orientation of our orbit gradually shifts relative to the galaxy's overall structure. This wobbling motion provides crucial information about our galaxy's hidden architecture. By measuring how our orbit precesses, astronomers can determine how matter is distributed throughout the galaxy, including the invisible dark matter. The wobble also means our solar system experiences a very gradual tour of slightly different galactic environments over cosmic time. We slowly sample different vertical levels within the galaxy's disk and different orientations relative to spiral arms. Even the subtle wobbles in our cosmic path reveal secrets about the invisible forces that shape our entire galaxy. Our solar system doesn't live on one of the galaxy's main highways. We live on a cosmic side street. Most people imagine we sit in one of the galaxy's major spiral arms. Those prominent curved structures visible in photos of other galaxies. The reality is far more humble. We live in what astronomers call the Orion Spur. A spur is basically a minor branch that connects two major galactic highways. Think of it as a cosmic on-ramp linking bigger structures. The Orion Spur stretches between two major spiral arms called the Sagittarius Arm and the Perseus Arm. This local spiral arm is much smaller and less dense than the galaxy's main spiral features. It contains far fewer massive stars, less active star formation, and lower levels of cosmic chaos. Our location on this minor spur explains a lot about our cosmic environment. We're close enough to the galactic action to benefit from previous generations of star formation. But we're far enough from the main spiral arms to avoid their more dangerous aspects. Living on a galactic side street has given our solar system the perfect balance of cosmic enrichment and cosmic safety. Spiral arms blaze across the galaxy like cosmic lighthouses because they're where most new stars are born. These regions contain vast clouds of gas and dust, the raw materials for making stars. When these clouds get compressed by the spiral arm's gravitational effects, they collapse and ignite into brilliant new suns. The newest stars burn incredibly hot and bright. Young, massive stars pump out intense blue and ultraviolet light that makes spiral arms glow dramatically in photographs. These stellar giants live fast and die young, burning through their fuel in just a few million years before exploding as supernovas. This constant cycle of stellar birth and death makes spiral arms both beautiful and dangerous. The radiation from young massive stars can sterilize planets. The shock waves from supernova explosions can destroy atmospheric chemistry. Our position in a minor spur means we experience much less of this stellar violence. We get the benefits of heavy elements created by previous stellar generations without getting fried by their explosive deaths. Spiral arms are cosmic nurseries where stars are born, but they're also cosmic war zones where stars die violently. What if the galaxy's spiral arms aren't actually physical objects at all? Modern astronomy suggests they're more like waves moving through space, regions where matter temporarily piles up before spreading out again. Scientists call this the density wave theory. It explains spiral arms as traveling waves of compression that move through the galaxy's disk much slower than the stars themselves. Imagine cosmic traffic getting backed up at a slow-moving construction zone. Stars flow into the density wave from behind, slow down temporarily as they pass through the compressed region, then speed up again as they exit the other side. The traffic jam moves slowly around the galaxy, while individual stars zip through it relatively quickly. This means our solar system periodically passes through these spiral density waves. Each passage exposes us to different conditions: higher stellar density, more active star formation, increased radiation levels. Between spiral arm passages, we cruise through quieter regions with less cosmic activity. These calm periods might provide crucial breaks that allow planetary systems to maintain stable conditions. Our solar system rides through the galaxy like a car passing through slow-moving traffic jams separated by stretches of open highway. Could our journey through the galaxy's spiral arms be written in Earth's fossil record? Some scientists think cosmic cycles might influence evolution itself. Every 140 million years or so, our solar system passes through one of the galaxy's major spiral arms. These passages expose Earth to increased cosmic radiation from young massive stars and frequent supernova explosions. The timing is eerily suspicious. Geologists have identified several major mass extinction events in Earth's history. Some of these catastrophic periods coincide roughly with when our solar system should have been passing through spiral arms. The connection isn't proven, but the mechanism makes sense. Increased cosmic radiation could damage Earth's ozone layer, allowing deadly ultraviolet light to reach the surface. Nearby supernova explosions could bombard our atmosphere with high-energy particles. These cosmic assaults wouldn't necessarily kill everything on Earth, but they could stress ecosystems enough to trigger evolutionary changes and species turnover. The rise and fall of species on Earth might be connected to our solar system's journey through the galaxy's most active regions. Right now, we're cruising through one of the galaxy's safest neighborhoods. Our current location sits between major spiral arms in what astronomers call the inter-arm region. These cosmic suburbs experience far less stellar violence than the main spiral arms. Fewer massive stars means fewer supernova explosions. Lower stellar density means less gravitational chaos. Reduced star formation means lower radiation levels. We're essentially living in a galactic nature preserve. This calm environment has persisted for millions of years, providing Earth with stable cosmic conditions during a crucial period of evolutionary development. Complex life forms had time to evolve without getting repeatedly hammered by cosmic catastrophes. The inter-arm regions aren't completely empty or inactive. They still contain plenty of older, more stable stars, but they lack the cosmic fireworks that make spiral arms so dangerous for life. Our current address in this quiet zone might be one of the reasons Earth has maintained such a rich biosphere for so long. Sometimes the most important cosmic real estate is the boring stuff between the action-packed neighborhoods. Here's something that will blow your mind. The galaxy's spiral arms rotate at a completely different speed than the stars do. This creates one of the weirdest aspects of galactic astronomy. Stars orbit the galactic center roughly twice as fast as the spiral arm pattern rotates. It's like cosmic traffic moving through a slow-moving construction zone. Stars catch up to spiral arms from behind, pass through them, then leave them behind. This means spiral arms aren't permanent collections of the same stars. They're temporary traffic jams where different stars pile up at different times. The stars that make a spiral arm bright today will be completely different from the stars that made it bright 50 million years ago. Our solar system follows this same pattern. We approach spiral arms from behind, spend time passing through their denser regions, then emerge into the quieter inter-arm spaces. The whole cycle takes roughly 100 million years. We spend about 10 million years actually inside a major spiral arm, then 90 million years cruising through calmer regions. We're cosmic commuters who periodically pass through the galaxy's busiest intersections before returning to the suburbs. Our local spiral arm doesn't exist in isolation. The Orion Spur connects to the galaxy's larger spiral structure through a complex network of branches and spurs. Mapping these connections required decades of careful observation. Dense cosmic dust blocks our view in many directions, making it nearly impossible to trace spiral arm structures from our location inside the galaxy. Advanced telescopes finally revealed the bigger picture. The Orion Spur appears to be a major branch connecting the Sagittarius arm to the Perseus arm, but it's not just a simple bridge. The structure includes multiple sub-branches, density variations, and complex interactions with other nearby spiral features. Some sections of our local arm contain more gas and dust. Others are dominated by older stars. Still others show active star formation in small, scattered regions. This complex structure means our cosmic neighborhood has varied characteristics depending on exactly where we are within the Orion Spur. We experience different local conditions as we orbit through different parts of our spiral arm. Our cosmic address sits within a branching network of stellar highways that connect the galaxy's major traffic arteries. Spiral arms don't just organize existing matter. They actively create the conditions where new solar systems can form. When gas and dust clouds encounter a spiral arm's density wave, they get compressed by shock waves traveling through space. These cosmic compression waves trigger the collapse of gas clouds that might otherwise remain stable for millions of years. This compression process is what transforms raw cosmic material into new stars and planetary systems. The shock waves work like cosmic bulldozers, pushing material together until it reaches the critical density needed for gravitational collapse. Once collapse begins, the compressed regions fragment into multiple smaller clumps that eventually become individual star systems. Our own solar system likely formed in exactly this type of environment. Ancient spiral arm passage may have triggered the collapse of the gas cloud that eventually became our sun and planets. The heavy elements incorporated into Earth and the other rocky planets were forged inside massive stars that lived and died in previous spiral arm passages. Those stellar deaths enriched the local gas clouds with the materials needed to build planets like Earth. Spiral arms are cosmic factories where the raw materials of solar systems get processed into the building blocks of worlds. As our solar system travels through different galactic regions, we encounter constantly changing magnetic fields that affect our entire cosmic neighborhood. The galaxy has its own magnetic field, invisible lines of magnetic force that thread through space between the stars. This galactic magnetic field isn't uniform. It varies dramatically between spiral arms and interarm regions. Spiral arms contain much stronger and more turbulent magnetic fields due to their active star formation and stellar winds from massive young stars. Interarm regions have weaker, more organized magnetic fields. These changes affect our solar system in subtle but important ways. Our Sun creates its own magnetic bubble called the heliosphere that surrounds the entire solar system. This bubble acts like a cosmic windshield, deflecting some of the harmful cosmic radiation that constantly streams through space. When we pass through regions with different galactic magnetic fields, the shape and effectiveness of our heliosphere changes. Stronger external magnetic fields can compress our protective bubble. Weaker fields allow it to expand. These variations might influence the amount of cosmic radiation that reaches Earth's atmosphere, potentially affecting climate and atmospheric chemistry over long time periods. Our solar system's magnetic environment constantly changes as we journey through the galaxy's varied magnetic landscape. In roughly 50 million years, our solar system may enter the next major spiral arm, and everything about our cosmic environment may change. Astronomical calculations suggest our next destination could be the Perseus Arm, one of the galaxy's most prominent spiral features. This region contains far more massive stars, active star formation, and cosmic violence than our current quiet neighborhood. The transition won't happen overnight. As we approach the Perseus Arm, we'll gradually encounter increased stellar density, higher radiation levels, and more frequent supernova explosions. The changes will build slowly over millions of years. Earth will experience these cosmic changes as increased levels of cosmic radiation reaching our atmosphere. This could affect global climate patterns, atmospheric chemistry, and possibly even evolutionary pressures on life. But the changes won't necessarily be catastrophic. Earth has survived multiple spiral arm passages throughout its history. Life has proven remarkably adaptable to changing cosmic conditions. The Perseus Arm passage might even bring benefits. Increased cosmic radiation could trigger cloud formation that leads to global cooling. Nearby stellar explosions could enrich our local space with fresh, heavy elements. Our solar system's next major cosmic adventure is already scheduled. We just need to wait 50 million years for it to begin. While our solar system races around the galaxy, it also rides a much slower cosmic roller coaster. We constantly move up and down relative to the galaxy's main disk in a gentle oscillating motion. This vertical bobbing motion follows a predictable cycle. Every 33 million years, we complete one full up and down cycle relative to the galaxy's central plane. Right now, we're positioned slightly above the galactic disk and moving southward. Think of the galaxy as a giant cosmic pancake with most of the stars, gas, and dust concentrated in the flat middle layer. Our solar system doesn't travel exactly along this central plane. Instead, we follow a wavy path that carries us above and below it in regular cycles. This oscillation isn't random or chaotic. It's a fundamental part of our orbital mechanics, as predictable as the seasons on Earth. The motion happens so slowly that hundreds of human generations pass during each phase of the cycle. The timing of this cosmic roller coaster has remained remarkably stable throughout our solar system's entire history. We've completed roughly 150 complete oscillation cycles since Earth formed. Our journey through the galaxy includes a gentle vertical dance that has been going on for over 4 billion years. What keeps our solar system from drifting away from the galaxy's main disk forever? The answer lies in a cosmic restoring force that works like an invisible rubber band. The galaxy's main disk contains most of its visible matter: stars, gas clouds, and cosmic dust. All this material creates a gravitational field that acts like a cosmic magnet, constantly tugging objects back toward the central plane. When our solar system drifts above the galactic disk, gravity pulls us back down. When we drift below it, gravity pulls us back up. This creates what physicists call simple harmonic motion, the same type of motion you see in a pendulum or a bouncing spring. The farther we get from equilibrium, the stronger the restoring force becomes. The gravitational restoring force isn't strong enough to jerk us around violently. Instead, it provides a gentle but persistent pull that gradually curves our path back toward the galactic center plane. This cosmic rubber band effect ensures that our vertical oscillations remain bounded and predictable. Without it, we might drift so far from the galactic disk that we'd become cosmic outcasts wandering through empty space. Gravity acts as our cosmic safety net, ensuring we never stray too far from the galaxy's main neighborhood. Our vertical motion through space follows one of nature's most elegant mathematical patterns. We trace out what mathematicians call a sine wave, the same smooth, flowing curve you see in ocean waves. This sine wave motion has very specific limits. We never venture more than about 250 light-years above or below the galaxy's central plane before the gravitational restoring force turns us around. The pattern is almost perfectly predictable. At the top and bottom of each oscillation, our vertical velocity drops to zero before reversing direction. At the midpoint, when we cross through the galactic plane, our vertical speed reaches maximum. This creates a smooth, rhythmic motion that astronomers can calculate with incredible precision. We know exactly where our solar system was in its vertical cycle 100 million years ago, and exactly where it will be 100 million years from now. The mathematical beauty of this motion reflects the underlying physical laws that govern all orbital mechanics. From planetary orbits to galactic oscillations, the same elegant mathematics describes motion throughout the universe. Our cosmic dance follows mathematical rules so precise that we can predict our position millions of years into the future. Every 33 million years, our solar system plunges through the galaxy's main disk like a submarine diving through a layer of dense underwater fog. The galactic disk contains far more matter than the empty space above and below it. Stars pack more closely together. Gas clouds become thicker and more numerous. Cosmic dust accumulates in higher concentrations. When we pass through this denser environment, everything changes. The increased matter density compresses our sun's protective magnetic bubble, the heliosphere that normally shields us from harmful cosmic radiation. This cosmic windshield gets squeezed smaller, potentially allowing more dangerous particles to penetrate closer to Earth. Our solar system also encounters more gravitational disturbances during these passages. Dense gas clouds and nearby stars create additional tugs and pulls that can subtly alter the orbits of comets and asteroids in our outer solar system. These disk passages don't last long in cosmic terms, perhaps a few million years out of each 33 million year cycle, but they represent periods of increased cosmic stress for our entire solar system. Every trip through the galaxy's main disk exposes us to a denser, more chaotic cosmic environment that tests our solar system stability. Far beyond Pluto, in the frozen outer reaches of our solar system, lies a vast spherical cloud of comets called the Oort cloud. Our vertical oscillations through the galaxy regularly disturb this distant comet reservoir. The Oort cloud contains trillions of icy objects left over from our solar system's formation. These cosmic snowballs orbit so far from the Sun that they're barely held by our solar system's gravity. Our galactic oscillations create subtle but important changes in the gravitational environment that reaches the Oort cloud. As we move through different vertical positions relative to the galaxy, the tidal forces from the galaxy's gravity vary slightly. These tiny changes can nudge Oort cloud comets just enough to alter their orbits. Some comets get pushed into elongated orbits that eventually bring them into the inner solar system as visible comets. Others get pushed outward and escape our solar system entirely. This process might explain why Earth experiences periods with more frequent comet impacts followed by quieter periods. The timing of our galactic oscillations could influence the rate at which new comets get delivered to the inner solar system. Our vertical journey through the galaxy acts like a cosmic spoon, occasionally stirring up our solar system's distant comet cloud. As our solar system oscillates up and down through the galaxy, we encounter completely different types of stellar neighbors. The galaxy's disk isn't uniform from top to bottom. Different types of stars prefer different vertical levels, creating distinct cosmic neighborhoods at various heights above and below the galactic plane. Near the central disk, we encounter younger, more massive stars that burn hot and bright but die quickly. These stellar giants rarely stray far from their birthplaces in the galaxy's dense central region. 2. As we rise above or sink below the disk, we meet older, smaller stars that have had billions of years to migrate away from the galactic center. These stellar seniors burn more slowly and live much longer than their flashy younger cousins. The stellar population changes also affect the local radiation environment. Young massive stars pump out intense ultraviolet light and eventually explode as supernovas. Older stars provide a much calmer, more stable cosmic environment. Our current position slightly above the galactic plane means we're surrounded primarily by middle-aged stars similar to our Sun. This creates a relatively peaceful cosmic neighborhood with moderate radiation levels. Our vertical position in the galaxy determines what kind of stellar community we live in at any given time. Our solar system doesn't oscillate alone through the galaxy. Most nearby stars participate in the same vertical dance, creating a coordinated cosmic ballet. Stars that formed in the same galactic region tend to have similar oscillation patterns. They rise and fall together through the galaxy's disk like synchronized swimmers moving in formation. This collective motion reveals important clues about our cosmic origins. The fact that nearby stars share similar oscillation cycles suggests they all formed from the same general population of galactic matter. We're part of a stellar generation that condensed from gas clouds with similar gravitational histories. Some stellar neighbors oscillate with slightly different periods or amplitudes, indicating they originated in different parts of the galaxy or formed at different times. But the overall pattern shows clear evidence of shared galactic ancestry. This stellar choreography also means our local cosmic environment remains relatively stable even as we oscillate through the galaxy. We don't randomly encounter completely different stellar populations during our vertical journey. We're part of a stellar community that moves through the galaxy together, maintaining familiar cosmic neighborhoods even as our vertical position changes. Some scientists have discovered a disturbing pattern linking our solar system's galactic oscillations to major extinction events in Earth's fossil record. Geological evidence shows that life on Earth has experienced several devastating mass extinction events over the past few 100 million years. These catastrophic periods wiped out large percentages of all species alive at the time. The timing of some extinctions roughly matches our 33 million-year oscillation cycle. The correlation isn't perfect, and many extinction events clearly have other causes like asteroid impacts or volcanic eruptions. But the statistical pattern is strong enough to suggest our galactic position might influence Earth's biological stability. The proposed mechanism involves increased cosmic radiation during certain phases of our oscillation cycle. When we pass through the galactic disk or encounter regions with more active star formation, Earth might receive higher doses of harmful cosmic rays. This increased radiation could damage Earth's ozone layer, allowing deadly ultraviolet light to reach the surface. It might also trigger climate changes by affecting atmospheric chemistry and cloud formation patterns. Our journey through the galaxy might be written in Earth's fossil record as periodic stress events that reshape the evolution of life itself. Most people imagine our solar system following a simple circular path around the galaxy. The reality is far more complex and beautiful. When you combine our circular orbit around the Galactic Center with our vertical oscillations through the galactic disk, the result is a three-dimensional spiral trajectory that looks like a cosmic corkscrew. We're simultaneously moving forward, sideways, and up and down through space. This complex motion means our solar system never repeats exactly the same path through the galaxy. Each orbit carries us through slightly different cosmic environments as our vertical position shifts relative to the galactic disk. The three-dimensional nature of our trajectory also means we sample a much wider variety of galactic environments than we would with simple circular motion. We experience different stellar densities, radiation levels, and gravitational influences throughout each galactic orbit. Mapping this complex path requires sophisticated computer simulations that track multiple gravitational influences over billions of years. The calculations reveal that our spiral trajectory has remained remarkably stable despite countless gravitational perturbations. Our true path through the galaxy traces out an elegant three-dimensional spiral that carries us through an ever-changing cosmic landscape. During the highest peaks of our vertical oscillations, our solar system ventures into one of the galaxy's most mysterious regions, the galactic halo. The halo surrounds our entire galaxy like a vast spherical shell extending far beyond the main disk. This region contains very few normal stars, but harbors most of the galaxy's mysterious dark matter. For brief periods during each oscillation cycle, we become temporary halo residents. The halo environment differs dramatically from the galactic disk. Stellar neighbors become incredibly rare. The local matter density drops to nearly empty space. We encounter ancient globular clusters, some of the oldest objects in the universe. These excursions into halo territory expose us to a completely different gravitational environment dominated by dark matter rather than normal stellar matter. The change might subtly affect the orbits of objects in our outer solar system. The halo also contains streams of stars and gas from smaller galaxies that our Milky Way has captured and disrupted over billions of years. During our highest oscillations, we might pass near some of these galactic debris flows. Our vertical oscillations occasionally carry us beyond the galaxy's main neighborhood into the mysterious frontier regions where dark matter rules. Our vertical oscillations happen much faster than our orbit around the galaxy, creating an interesting rhythm in our cosmic motion. One complete galactic orbit takes roughly 200 million years. One complete vertical oscillation takes only 33 million years. This means we complete about 6 up and down cycles during each trip around the galaxy. The speed difference creates a complex pattern of motion. Think of it like a roller coaster that also travels around a giant circular track. The up and down motion happens multiple times during each complete lap around the track. This timing relationship means our solar system experiences a repeating cycle of cosmic environments during each galactic orbit. We encounter similar combinations of galactic disk passages and halo excursions every 200 million years, but with slight variations due to the galaxy's own evolution. The multiple oscillation cycles also provide a form of cosmic insurance. If one disk passage happens to coincide with particularly dangerous galactic conditions, we don't have to wait 200 million years for different circumstances. The next oscillation cycle might provide safer conditions. Our cosmic motion combines slow galactic orbits with faster vertical oscillations, creating a complex rhythm that repeats every few 100 million years. Space between the stars isn't actually empty. Our solar system currently travels through a region of warm, thin gas called the local interstellar cloud. This cosmic cloud stretches for dozens of light years in every direction around us. It contains roughly 1 atom per cubic centimeter, which sounds like nothing, but is actually quite dense for interstellar space. The cloud consists mainly of hydrogen and helium left over from ancient stellar explosions. The local interstellar cloud is both warmer and thinner than the average interstellar material found elsewhere in the galaxy. Temperatures reach about 6,000 degrees Celsius, hot enough to melt copper, but so thin that a spacecraft could fly through it without feeling any heat. This cloud material constantly streams past our solar system as we move through it at tremendous speed. The interaction between this flow and our sun's magnetic field determines the size and shape of our protective magnetic bubble. We've been traveling through this particular cloud for tens of thousands of years, and will remain inside it for thousands more, before emerging into a different interstellar environment. Our solar system is completely immersed in a sea of hot, thin gas that affects everything from our magnetic environment to the cosmic radiation that reaches Earth. What if I told you that our solar system sits inside a gigantic bubble blown by cosmic explosions millions of years ago? Astronomers call our current location the local bubble, a region of space that's much hotter and emptier than the surrounding galaxy. This bubble stretches for hundreds of light years in every direction. Multiple massive stars exploded as supernovas in this region long before our solar system arrived. These stellar death explosions blasted away most of the normal interstellar gas and dust, creating a cavity in space. The supernova shock waves heated the remaining gas to over 1,000,000 degrees Celsius, while making it thousands of times thinner than normal interstellar material. The result is a vast region of superhot but extremely thin cosmic gas. Living inside this bubble provides our solar system with some important advantages. The thin gas creates less resistance to our motion through space. The lack of dense dust clouds gives us clearer views of distant galaxies and cosmic objects. But the bubble environment also exposes us to more cosmic radiation from distant sources, since there's less interstellar material to absorb harmful high-energy particles. We're traveling through a cosmic cavity carved by ancient stellar explosions that died out long before Earth even formed. Neutral hydrogen atoms from interstellar space can do something that most cosmic material cannot. They can sneak past our solar system's magnetic defenses and penetrate all the way to Earth's neighborhood. Most interstellar material carries an electric charge that makes it interact strongly with magnetic fields. Our Sun's magnetic bubble deflects this charged material around our solar system like a cosmic windshield. Neutral hydrogen atoms have no electric charge at all. This means they ignore magnetic fields completely and flow straight through our solar system's protective barriers. They travel in straight lines from interstellar space directly into the inner solar system. These invisible atomic invaders don't pose any danger to planets or spacecraft. Individual hydrogen atoms are incredibly tiny and harmless, but their ability to penetrate our defenses makes them valuable scientific messengers. By studying neutral hydrogen atoms reaching Earth, astronomers can determine the composition, temperature, and motion of the interstellar cloud surrounding our solar system. These atoms carry direct information from the cosmic environment outside our magnetic bubble. Neutral hydrogen atoms act like cosmic spies that slip past our solar system's defenses to deliver intelligence about the interstellar environment around us. Our solar system doesn't exist in magnetic isolation. The Sun's magnetic field constantly battles with magnetic fields from interstellar space, creating complex interactions that shape our cosmic environment. Interstellar space has its own magnetic field, threading through the galaxy between the stars. This galactic magnetic field isn't uniform. Its strength and direction vary dramatically depending on our location within different cosmic structures. When our solar system's magnetic field meets interstellar magnetic fields, they don't simply cancel each other out. Instead, they create complex boundary regions where magnetic field lines get twisted, compressed, and reconnected in violent processes that release bursts of energy. These magnetic interactions affect the shape and size of our protective heliosphere. Sometimes the external magnetic field reinforces our Sun's field, creating a larger protective bubble around our solar system. Other times, conflicting magnetic orientations compress our heliosphere and reduce its protective effectiveness. These magnetic field interactions also influence how cosmic radiation from distant sources penetrates into our solar system. Stronger external fields can deflect more harmful particles away from us. Our solar system's magnetic environment constantly changes as we encounter different interstellar magnetic field configurations during our galactic journey. Tiny dust particles from interstellar space manage to infiltrate our solar system despite our Sun's powerful solar wind trying to blow them away. These cosmic dust grains are incredibly small, each one smaller than the particles in cigarette smoke. They consist of various materials including carbon, silicon, and iron that condensed around dying stars millions of years ago. Most interstellar dust gets deflected or slowed down by our solar system's magnetic barriers. But some particles have just the right size and charge to slip through our defenses. They follow complex curved paths as they interact with our magnetic field, but they don't get completely blocked. The dust particles that make it through contribute to the overall dust environment throughout our solar system. Spacecraft detectors have measured this interstellar dust component mixed in with dust created by comets and asteroids within our own system. Studying these cosmic dust infiltrators helps scientists understand the composition and history of the interstellar medium surrounding us. Each dust grain carries information about stellar processes that occurred in distant parts of the galaxy. Our solar system's dust environment includes visitors from deep space that manage to sneak past our cosmic border controls. The direction our solar system travels through interstellar space creates a cosmic weather pattern that affects our entire magnetic environment. We're moving through the local interstellar cloud at roughly 25 kilometers per second, about 56,000 miles per hour. This creates a headwind of interstellar material flowing past us in the opposite direction. Just like driving through rain makes droplets hit your windshield from the front, our motion through space creates an asymmetric flow pattern around our solar system. The leading edge of our heliosphere, the side facing our direction of motion, gets compressed by this cosmic headwind. Interstellar material piles up against our magnetic field like water building up in front of a speedboat. The trailing edge experiences much less pressure, allowing our magnetic bubble to expand farther in that direction. This creates a comet-like shape with a compressed head and an elongated tail. This asymmetric shape affects how cosmic radiation reaches different parts of our solar system. The compressed leading edge provides better shielding, while the expanded trailing region offers less protection from harmful particles. Our solar system's motion through interstellar space creates a cosmic weather pattern with distinct upstream and downstream effects on our protective magnetic environment. The gas cloud surrounding our solar system carries chemical clues about the stellar explosions and cosmic processes that shaped our galactic neighborhood over millions of years. Interstellar material isn't just hydrogen and helium left over from the Big Bang. It's been enriched with heavier elements forged inside stars and dispersed by stellar explosions throughout galactic history. The local interstellar cloud contains measurable amounts of carbon, nitrogen, oxygen, and other elements created by nuclear fusion inside massive stars. But the chemical composition differs significantly from our solar system's composition. This tells us that our current interstellar environment formed from stellar processes that occurred at different times and places than the stellar explosions that enriched the gas cloud that eventually became our sun and planets. Some elements appear in different ratios than we see in our solar system, indicating that different types of stellar explosions contributed to the local interstellar medium. The pattern suggests contributions from both massive star supernovas and smaller stellar explosions. These chemical differences provide a cosmic archaeology record that helps astronomers reconstruct the history of star formation and stellar death in our corner of the galaxy. The chemical composition of our interstellar environment tells the story of ancient stellar explosions that occurred long before our solar system formed. Cosmic rays. High-energy particles streaming through space from distant stellar explosions don't travel in straight lines when they encounter our local interstellar environment. These cosmic bullets race through space at nearly the speed of light, carrying tremendous energy from supernova explosions, black hole jets, and other violent cosmic events scattered throughout the galaxy. The local interstellar cloud's magnetic field acts like an invisible lens that bends and focuses these particle streams. Charged cosmic ray particles follow curved paths when they encounter magnetic fields. The interstellar magnetic field in our local environment deflects cosmic rays coming from certain directions while allowing others to pass through more easily. This cosmic ray lensing effect means Earth receives different amounts of cosmic radiation depending on which direction the particles originally came from. Some cosmic sources appear brighter in cosmic rays than others due to magnetic focusing effects. The deflection patterns also change as our solar system moves through regions with different magnetic field orientations. This creates time variations in the cosmic ray environment that spacecraft and ground-based detectors can measure. The invisible magnetic fields threading through our interstellar neighborhood act like cosmic lenses that focus and defocus streams of high-energy particles from across the galaxy. Every few thousand years, our solar system crosses from one interstellar cloud into another, causing sudden changes in our cosmic environment. These transitions between different interstellar regions can happen relatively quickly in cosmic terms. Within a few thousand years, we can move from one type of interstellar environment into something completely different. The boundary crossings bring dramatic changes in density, temperature, magnetic field strength, and chemical composition of the material surrounding our solar system. When we enter a denser interstellar cloud, our heliosphere gets compressed dramatically. The increased external pressure can shrink our protective magnetic bubble to a fraction of its normal size, potentially allowing more cosmic radiation to reach the inner solar system. Transitions into regions with stronger magnetic fields can also compress our heliosphere while deflecting cosmic radiation in new patterns. The combined effects might influence Earth's climate by altering the amount of cosmic rays reaching our atmosphere. Some scientists suggest these interstellar boundary crossings might correlate with ice age cycles on Earth, though the connection remains controversial and unproven. Our solar system periodically experiences cosmic environmental shock as we cross boundaries between fundamentally different interstellar neighborhoods. The interstellar environment around our solar system isn't smooth and uniform. It's filled with turbulent eddies and swirls that constantly change the local conditions we encounter. Interstellar turbulence works like atmospheric weather, but on scales of light years and time scales of thousands of years. Density fluctuations, magnetic field tangles, and temperature variations create a constantly shifting cosmic landscape. These turbulent structures affect our solar system's magnetic environment in unpredictable ways. Sometimes we encounter regions where interstellar material flows in chaotic patterns rather than smooth streams. These turbulent zones can cause our heliosphere to fluctuate in size and shape over periods of decades to centuries. Magnetic field variations within turbulent regions can also create temporary increases or decreases in cosmic ray shielding. Our protection from galactic radiation varies as we move through different turbulent cells. The turbulence also affects how efficiently our solar system mixes with the surrounding interstellar medium. Some turbulent configurations enhance the penetration of interstellar material into our solar system, while others provide better isolation. Our local cosmic environment resembles a turbulent ocean, where we constantly encounter changing currents, eddies, and waves on scales far larger than our entire solar system. Complex molecules from interstellar space occasionally penetrate our solar system's defenses, bringing samples of sophisticated cosmic chemistry from the void between stars. Interstellar space contains surprisingly complex molecules formed through chemical processes in cold gas clouds and around dying stars. Water molecules, carbon monoxide, methanol, and even organic compounds float through the galaxy. Most of these molecules get destroyed by our sun's intense radiation and solar wind before they can penetrate deep into our solar system. But some molecular species are hardy enough to survive the journey into our cosmic neighborhood. They arrive in tiny quantities, perhaps a few molecules per cubic meter, but they represent direct samples of interstellar chemistry. These molecular visitors carry information about chemical processes occurring in the cold depths of space far from any star. They reveal that complex chemistry happens throughout the galaxy, not just around stars and planets. Some of the molecules detected include the same types of organic compounds that might have contributed to the development of life on early Earth. This suggests that the raw materials for life might be common throughout interstellar space. Our solar system occasionally receives molecular mail from deep space carrying news about the complex chemistry happening in the cosmic void. In roughly 50,000 years, our solar system will exit the local interstellar cloud and enter a completely different cosmic environment. Computer models predict our future path will carry us into a region with fundamentally different properties than our current interstellar neighborhood. The new environment might be denser, cooler, and have stronger magnetic fields. This transition will dramatically alter our solar system's interaction with the surrounding cosmic medium. A denser interstellar environment would compress our heliosphere much more severely, potentially shrinking our protective magnetic bubble to less than half its current size. This could allow significantly more cosmic radiation to penetrate the inner solar system. Changes in the interstellar magnetic field orientation might also affect how cosmic rays reach Earth. The new configuration could either enhance or reduce our protection from galactic radiation sources. The chemical composition of the new interstellar environment might differ substantially from our current location, providing new information about stellar processes that occurred in different parts of our galactic neighborhood. Earth's climate might experience subtle influences from these changing cosmic conditions, though the effects would be much smaller than natural climate variations caused by solar activity and volcanic eruptions. Our solar system's future cosmic environment will be as different from today's conditions as our current location differs from the environments we traveled through thousands of years ago. Computer simulations reveal a startling truth about our solar system's origins. We didn't form where we live today. When astronomers reverse calculate our orbital history using gravitational models, they discover that our solar system was born much closer to the galactic center than our current position. 4.5 billion years ago, our birthplace sat thousands of light years closer to the galaxy's chaotic core. This intergalactic region would have been far more dangerous than our current cosmic neighborhood. Higher stellar density meant more frequent close encounters with other stars. More massive stars meant more supernova explosions. Stronger radiation fields could have prevented planets from developing stable atmospheres. Yet somehow our solar system not only survived these harsh conditions but gradually migrated outward to our current safe location in the galactic suburbs. The outward migration happened incredibly slowly. Our orbit expanded by only a few light years every million years. This glacial movement was caused by gravitational interactions with other stars and cosmic structures over billions of years. Our solar system has spent billions of years slowly escaping from the galaxy's dangerous inner neighborhoods toward the relative safety of our current cosmic address. How many times has our solar system run the gauntlet through the galaxy's most violent stellar neighborhoods? Astronomical calculations suggest we've survived at least 20 major spiral arm passages since Earth formed. Each passage exposed our solar system to dramatically different cosmic conditions than we experience in our current quiet inter-arm location. Spiral arms contain the galaxy's most active star formation regions, where massive stars are born, live briefly, and die in spectacular supernova explosions. During our spiral arm transits, Earth would have experienced significantly higher levels of cosmic radiation. Nearby supernova explosions might have temporarily damaged our planet's ozone layer, allowing harmful ultraviolet radiation to reach the surface. Some of these passages coincided with major geological and biological changes in Earth's history. Increased cosmic radiation might have influenced mutation rates and evolutionary pressures on early life forms. The remarkable thing is that life not only survived these cosmic assaults, but may have benefited from them. Moderate increases in radiation can drive evolutionary innovation by increasing genetic diversity. Our solar system has repeatedly weathered cosmic storms that would terrify any civilization, emerging each time into calmer galactic waters with Earth's biosphere intact. Several times in our solar system's history, other stars have passed close enough to gravitationally disturb the orbits of comets and asteroids in our outer regions. These stellar close encounters don't happen often, but when they do, they can dramatically reshape the outer architecture of our solar system. A passing star can nudge thousands of comets from the distant Oort cloud onto paths that bring them into the inner solar system. The most recent significant encounter occurred roughly 70,000 years ago. A small red dwarf star called Scull's star passed within about 1 light year of our solar system, close enough to disturb the outer edges of our comet cloud. This cosmic near-miss sent a shower of comets toward the inner solar system that continued for thousands of years. Earlier encounters were likely more dramatic. Computer simulations suggest that larger stars passing even closer could have stripped away significant portions of our outer solar system's comet and asteroid populations. These gravitational disruptions may have delivered water and organic materials to the inner planets during crucial periods in Earth's development. The heavy bombardment periods recorded in lunar craters might represent the aftermath of stellar close encounters. Our solar system bears invisible scars from cosmic traffic accidents that occurred when neighboring stars passed too close for comfort. Our galaxy has devoured several smaller galaxies during our solar system's lifetime, yet we somehow survived the gravitational chaos of these cosmic cannibalism events. When a large galaxy like ours captures and dismantles a smaller galaxy, the gravitational disruption affects star orbits throughout the entire galactic disk. Stars get scattered. Orbital periods change, and some systems get ejected entirely into intergalactic space. Our solar system weathered multiple galactic merger events without catastrophic damage. The most recent major merger occurred roughly 10 billion years ago, before our solar system even formed. But smaller galactic snacks have been consumed more recently, including dwarf galaxies that were disrupted within the last few billion years. These merger events created streams of stars and debris that our solar system occasionally encounters during our galactic orbit. When we pass through these stellar debris fields, we experience slightly increased gravitational disturbances. The fact that our solar system maintained a stable orbit throughout these galactic upheavals demonstrates the remarkable resilience of orbital mechanics. Even major gravitational chaos affects individual star systems much less than you might expect. Our solar system has survived multiple galactic collisions that would have seemed like cosmic apocalypses to any observers, yet our planets still orbit peacefully around the same star. Our sun wasn't born alone. It formed as part of a stellar nursery containing hundreds or thousands of sibling stars, but time has scattered this cosmic family across the entire galaxy. Stars form in groups when giant gas clouds collapse and fragment into multiple stellar embryos. All the stars born in the same stellar nursery start with similar ages, chemical compositions, and initial orbital characteristics. But stellar families don't stay together forever. Gravitational interactions between newly formed stars gradually eject members from their birth clusters. Some stars gain energy and escape to higher galactic orbits. Others lose energy and spiral inward toward the Galactic Center. After 4.5 billion years, our solar system's stellar siblings are now scattered throughout a huge volume of galactic space. They might be anywhere within thousands of light years of our current position. Astronomers are actively searching for our sun's lost relatives by looking for stars with nearly identical chemical compositions and ages. Finding our stellar siblings would provide crucial information about the conditions in our birth cluster and the early history of our galactic neighborhood. The stars that shared our cosmic nursery are now spread across such vast distances that we might never identify our closest stellar relatives. Every 33 million years, our solar system plunges through the galaxy's main disk, and we've completed this journey roughly 150 times since Earth formed. Each passage through the galactic plane exposes our solar system to dramatically different conditions than we experience in the quieter regions above and below the main disk. The galactic plane contains higher densities of gas dust and stars that create increased gravitational disturbances and radiation exposure. During these crossings, our heliosphere gets compressed by denser interstellar material. More cosmic rays penetrate our solar system's magnetic defenses. Gravitational interactions with nearby stars and gas clouds become more frequent. Some scientists propose that these regular plane crossings might correlate with periodic mass extinction events on Earth. The timing isn't perfect, but there are suggestive patterns in the geological record. The remarkable aspect of these repeated crossings is how well our solar system has maintained its structural integrity. Despite 150 trips through the galaxy's most chaotic region, all our planets remain in stable orbits. Each plane crossing represents a cosmic stress test that our solar system has passed successfully for over 4 billion years. Our solar system has endured more than a century of passages through the galaxy's most disruptive region while maintaining the stable conditions that allowed complex life to evolve on Earth. Some of the meteorites that fall to Earth contain microscopic evidence of the different interstellar environments our solar system has traveled through over billions of years. These cosmic time capsules preserve tiny particles and chemical signatures from the various interstellar clouds, stellar winds, and cosmic radiation environments that our solar system has encountered during its galactic voyage. Ancient meteorites contain isotope ratios that reflect exposure to cosmic rays during different periods of our galactic journey. When our solar system passed through regions with higher cosmic ray intensities, the increased radiation created distinctive isotopic signatures in exposed materials. These signatures get preserved in meteorites that formed during those periods. Scientists can read these cosmic exposure records like tree rings, reconstructing the radiation environment our solar system experienced millions or billions of years ago. The isotopic evidence suggests our solar system has indeed traveled through varying cosmic environments with different levels of stellar activity, interstellar density, and radiation exposure. Some meteorites also contain presellar grains, microscopic particles that formed around other stars before our solar system even existed. These ancient stellar remnants provide direct samples of the interstellar medium that our birth cloud incorporated. Rocks falling from space carry a library of cosmic history that documents our solar system's billion-year journey through ever-changing galactic neighborhoods. Our sun's chemical composition tells the story of how our galactic neighborhood has changed over billions of years through successive generations of stellar death and birth. When our sun formed, it incorporated heavy elements created by previous generations of massive stars that lived, died, and exploded in our region of the galaxy. The concentration of these heavy elements, what astronomers call metallicity, reflects the cumulative history of stellar evolution in our cosmic neighborhood. Compared to very ancient stars formed when the galaxy was young, our sun is relatively rich in heavy elements like carbon, oxygen, silicon, and iron. This indicates that many stellar generations lived and died in our galactic region before our sun was born. But our sun's metallicity is lower than stars forming in the same galactic region today. This shows that stellar enrichment has continued in our neighborhood over the 4.5 billion years since our sun formed. The chemical evolution of our galactic environment has been driven by the steady accumulation of heavy elements from successive generations of dying stars. Each supernova explosion adds a new layer of heavy elements to the local interstellar medium. Our sun's chemical fingerprint preserves a record of the stellar deaths that enriched our cosmic neighborhood before our solar system was born. Earth's geological record contains radioactive smoking guns that prove massive stars have exploded relatively close to our solar system during our planet's history. Deep ocean sediments and ancient rock layers contain elevated levels of radioactive isotopes that could only have been created by nearby supernova explosions. The most compelling evidence comes from isotopes of iron-60, a radioactive form of iron with a half-life of 2.6 million years. Iron-60 doesn't occur naturally on Earth because it decays too quickly to have survived from Earth's formation. Any iron-60 found in geological layers must have arrived from space relatively recently in cosmic terms. Scientists have discovered multiple layers of iron-60 deposits in ocean sediments dating back several million years. The concentrations are too high to have come from distant cosmic sources. They require supernova explosions within roughly 300 light-years of our solar system. These isotopic signatures suggest that our solar system has experienced at least 2 episodes of nearby supernova activity in the past 10 million years. Each episode would have temporarily increased the cosmic radiation environment around Earth. The supernova events might have influenced Earth's climate by affecting atmospheric chemistry and cosmic ray exposure, though life clearly survived these cosmic fireworks displays. Earth's rocks preserve radioactive evidence that our solar system has repeatedly found itself in cosmic blast zones when nearby massive stars reached the end of their lives. Over billions of years, the galaxy's incredibly weak tidal forces have accumulated into measurable changes in our solar system's structure. Galactic tidal forces represent the difference in gravitational pull between the side of our solar system facing the galactic center and the side facing away. The effect is almost unimaginably tiny, less than 1 part in a trillion. But tiny forces can produce significant changes when given enough time. These gentle tidal forces have gradually altered the orbits of objects in our outer solar system over cosmic time scales. The effect is strongest on the most distant objects, where our sun's gravity is weakest. Computer simulations suggest that galactic tides have influenced the shape and orientation of the Oort cloud, our solar system's distant comet reservoir. The cloud's structure shows subtle asymmetries that match predictions for long-term tidal evolution. Galactic tides may also affect the long-term stability of the outer planets' orbits. Though these changes happen so slowly, they're barely detectable even with our most precise measurements. The cumulative effect of galactic tides demonstrates how cosmic forces operating on the largest scales can influence even the smallest details of planetary system architecture when given billions of years to operate. Forces so gentle they're almost undetectable have been quietly sculpting our solar system's architecture throughout its entire history. Right now, our entire solar system is headed toward a specific point in space near the bright star Vega, near the constellation Hercules. This cosmic destination isn't random. Our current motion through the galaxy carries us along a predictable path that astronomers can calculate with remarkable precision. The direction we're traveling is called our solar apex, the point in space that our sun appears to be moving toward relative to nearby stars. Vega won't always mark our destination. As we continue our journey over thousands of years, the patterns of stars in the sky will slowly shift. Constellations will change shape as stars move at different speeds through the galaxy. In 50,000 years, the bright star we're currently approaching will no longer occupy the same position relative to Earth's night sky. The entire stellar landscape will look completely different to any future observers. But our underlying motion through galactic space will continue following the same basic trajectory, carrying us toward whatever stars happen to occupy that region of space in the distant future. Our solar system follows a cosmic flight plan that points toward a specific region of space, even though the stellar landmarks along our route constantly change over cosmic time. In roughly 4.5 billion years, our entire galaxy will collide with the Andromeda Galaxy in the most violent cosmic event our solar system will ever experience. This isn't a gentle merger between cosmic neighbors. It's a full-scale galactic collision that will gravitationally scramble the orbits of billions of star systems, including ours. The Andromeda Galaxy is racing toward us at 250,000 miles per hour, growing larger in our telescopes every year as it approaches for this inevitable cosmic crash. When the collision begins, the gravitational chaos will reshape both galaxies completely. Our solar system's current orbit around the Galactic Center will be disrupted as competing gravitational fields battle for control. Computer simulations suggest several possible outcomes for our solar system. We might get ejected from the merged galaxy entirely, becoming wanderers in intergalactic space. We might spiral inward toward the new Galactic Center, or we might end up in a completely different type of orbit within the merged galaxy. The collision won't happen suddenly. The galaxies will pass through each other multiple times over hundreds of millions of years before finally settling into a single, larger elliptical galaxy. Our solar system's predictable galactic orbit has an expiration date when the cosmic collision of the century completely rewrites the rules of our cosmic neighborhood. Our sun won't remain the same forever, and its evolution will fundamentally change our solar system's motion through the galaxy. As our sun ages over the next 5 billion years, it will gradually lose mass through stellar winds, streams of particles constantly flowing away from its surface into space. This mass loss might seem trivial, but it has profound consequences for orbital mechanics. When the Sun loses mass, its gravitational pull on our entire solar system weakens. This causes all planetary orbits to expand slightly, and it affects our solar system's orbit around the galaxy as well. A less massive Sun means our solar system will move more slowly around the galactic center and follow a larger orbital path. We'll become less tightly bound to the galaxy's gravitational field. In the Sun's final stellar death throes, when it becomes a red giant star before shrinking into a white dwarf, it will lose roughly 40% of its current mass. This dramatic mass loss will significantly alter our galactic trajectory. The weakened gravitational connection to the galaxy might make our solar system more vulnerable to gravitational disruptions from passing stars or molecular clouds. Our Sun's inevitable death will literally lighten our gravitational load and change how tightly we're bound to our cosmic home galaxy. Roughly 50 million years from now, our solar system will enter the Perseus Arm, one of the galaxy's major spiral features packed with massive stars and violent stellar activity. This won't be like our current peaceful existence in the quiet interarm region between spiral structures. The Perseus Arm contains the kind of cosmic chaos that makes spiral arms dangerous places for planetary systems. Young massive stars in spiral arms burn incredibly hot and die spectacularly as supernovas within just a few million years of their birth. These stellar monsters pump out intense radiation that can strip away planetary atmospheres. Their explosive deaths create shock waves that travel for hundreds of light years through space. Our solar system will spend roughly 10 million years passing through this cosmic war zone before emerging into the next quiet interarm region. Earth might experience significantly increased cosmic radiation during this passage. The enhanced radiation could affect atmospheric chemistry, global climate patterns, and possibly even evolutionary pressures on life. However, life on Earth has already survived multiple spiral arm passages throughout our planet's history, suggesting that biospheres can adapt to these periodic cosmic stress events. Our next major cosmic adventure will take us through one of the galaxy's most active stellar neighborhoods where stars are born, live briefly, and die violently. Over billions of years, our solar system's orbital speed around the galaxy could gradually change due to cosmic forces beyond our control. The galaxy itself is evolving. Dark energy is tied to the universe's accelerating expansion, but gravity inside a galaxy still dominates the motions of stars and planetary systems. Our current orbital speed of roughly 500,000 miles per hour around the Galactic Center might not remain constant forever. Computer models predict gradual changes over billions of years. These shifts happen so slowly they're essentially imperceptible on human time scales. The change amounts to perhaps a few miles per hour every million years. But cosmic time scales make even tiny changes significant. Over billions of years, even a gentle drift can move us to a slightly different orbital radius as our orbit slowly evolves. The changing orbital characteristics might affect our solar system's interactions with spiral arms, since the timing of our passages through different galactic structures depends on our orbital period. Forces operating on cosmic scales will gradually modify our solar system's galactic dance moves over time periods that dwarf the entire history of complex life on Earth. Astronomical calculations reveal that several nearby stars will pass dangerously close to our solar system over the next few million years. These stellar encounters pose real threats to the stability of objects in our outer solar system. A passing star can gravitationally disrupt the Oort cloud, our distant reservoir of comets. sending thousands of icy objects toward the inner solar system. The closest predicted encounter involves a star called Gliese 710, which will pass within about 1 light-year of our solar system in roughly 1.3 million years. This stellar near-miss will be close enough to significantly perturb comet orbits in our outer solar system. Computer simulations predict an extended period of increased comet activity following this encounter. Other stars will pass at greater distances, but still close enough to cause measurable gravitational effects. The cumulative effect of multiple stellar encounters over millions of years could gradually alter the architecture of our solar system's outermost regions. These encounters might also affect the orbits of any undiscovered planets or large objects lurking in the distant outer solar system beyond Neptune. The increased comet activity could pose impact risks for Earth and other planets, though the probability of any individual comet hitting Earth remains extremely low. Our solar system's future includes a series of cosmic traffic encounters that will test the gravitational stability of our outermost regions. Under certain circumstances, our solar system could eventually break free from the Milky Way's gravity and become a wanderer in the vast emptiness between galaxies. Our current orbital speed keeps us safely bound to the galaxy, but this gravitational relationship isn't necessarily permanent over cosmic timescales. Multiple factors could potentially push our solar system toward the galactic escape velocity, the minimum speed needed to break free from the galaxy's gravitational hold. Cumulative gravitational encounters with other stars could gradually add energy to our galactic orbit. The Andromeda collision will dramatically redistribute orbital energy throughout both galaxies. Close passages near massive star clusters could provide additional gravitational kicks. If our orbital velocity increased beyond roughly 1.2 million miles per hour, we would begin spiraling outward toward the galactic edge and eventually into intergalactic space. Escaping the galaxy wouldn't necessarily be catastrophic for life on Earth. Our sun would continue shining normally, and planetary orbits would remain stable. But we would become cosmic exiles, isolated in the near-empty space between galaxies. The probability of galactic escape is low but not zero, especially considering the upcoming galactic collision and billions of years of potential gravitational encounters. Our solar system's gravitational lease on galactic citizenship could theoretically expire if the right combination of cosmic circumstances adds enough energy to our orbital motion. The interstellar environment surrounding our solar system will change dramatically as we continue our journey through different regions of galactic space. In roughly 50,000 years, we'll exit our current local interstellar cloud and enter a completely different type of cosmic neighborhood with altered physical properties. Future interstellar environments might have different densities, temperatures, magnetic field strengths, and chemical compositions than anything our solar system has experienced in recent cosmic history. Some regions might contain much denser material that would compress our heliosphere, the magnetic bubble protecting our solar system from cosmic radiation. Other regions might be nearly empty, allowing our protective bubble to expand far beyond its current size. Different magnetic field orientations in future interstellar environments could alter how cosmic rays reach our solar system. These changes might affect Earth's climate by influencing atmospheric chemistry and cloud formation patterns. We might also encounter stellar debris streams from ancient supernova explosions, regions enriched with heavy elements from recent stellar deaths, or areas swept clean by stellar winds from massive stars. Each new interstellar environment will test our solar system's ability to maintain stable protective barriers against the hostile radiation environment of deep space. Our future cosmic neighborhoods will expose our solar system to environmental conditions unlike anything we've experienced in millions of years of galactic travel. The supermassive black hole at our galaxy's center occasionally becomes violently active, and future outbursts could affect every star system in the galaxy, including ours. Currently, our galactic central black hole remains relatively quiet, consuming material at a steady but modest rate. But astronomical evidence shows that central black holes in other galaxies sometimes undergo dramatic feeding frenzies. When a supermassive black hole becomes highly active, it can blast jets of high-energy particles across the entire galaxy. These galactic-scale particle beams could dramatically increase radiation levels throughout our cosmic neighborhood. Enhanced cosmic ray bombardment might affect planetary atmospheres and climate systems throughout the galaxy. Active galactic cores also emit intense electromagnetic radiation that could influence star formation rates and the behavior of interstellar gas clouds across vast regions of galactic space. If our central black hole underwent such an activation event, the effects would propagate outward at the speed of light, taking roughly 26,000 years to reach our solar system's current location. The duration of such activity episodes can vary from thousands to millions of years, potentially exposing our solar system to enhanced radiation environments for geologically significant periods. The monster at our galaxy's heart could wake up at any time and transform the radiation environment throughout our cosmic home for millions of years. While the universe expands around us, our galaxy will become increasingly isolated from other galaxies in our cosmic neighborhood. The accelerating expansion of the universe, driven by mysterious dark energy, is gradually increasing the distances between galaxy groups throughout the cosmos. Over billions of years, galaxies beyond our immediate local group will disappear beyond the cosmic horizon, becoming unreachable no matter how fast we might travel. This cosmic isolation won't affect the internal structure of our galaxy or our solar system's motion within it. Gravity holds galactic structures together despite universal expansion. But the increasing isolation will have profound implications for the long-term evolution of our galactic environment. With fewer neighboring galaxies to interact with, our galaxy's future evolution will be determined primarily by internal processes. The reduced external gravitational influences might actually stabilize galactic rotation patterns and reduce the frequency of major gravitational disruptions. Future civilizations billions of years from now might inhabit a universe where only a handful of nearby galaxies remain visible, with the rest of the cosmos having expanded beyond the reach of light or travel. Universal expansion will transform our galaxy from a member of a cosmic community into an increasingly isolated island universe adrift in an expanding cosmic ocean. In the unimaginably distant future, our solar system faces an ultimate destiny determined by the longest-term cosmic processes in the universe. After our sun exhausts its nuclear fuel and becomes a cold white dwarf star, our planets will continue orbiting in the frozen darkness for trillions of years. Even in this stellar afterlife, our solar system will continue its galactic orbit, though the journey will become increasingly lonely as other stars meet similar fates. Eventually, gravitational interactions with other stellar remnants will either eject our planets into deep space or cause them to spiral into the white dwarf remnant of our Sun. The timescales involved are almost incomprehensible. These final gravitational rearrangements won't occur for roughly 100 trillion years, a period vastly longer than the current age of the universe. By this time, the galaxy itself will have evolved beyond recognition. Most stars will have died, leaving behind a sparse collection of stellar corpses orbiting in the darkness. Even the galaxy's central black hole will eventually evaporate through Hawking radiation over timescales so vast they make trillion-year periods seem brief. Our solar system's final chapter will be written in the ultimate cosmic twilight, when the universe itself approaches the end of its star-forming epoch. Billions of years from now, our galaxy will be a fundamentally different place that would be barely recognizable to observers familiar with today's Milky Way. Star formation will gradually decline as the galaxy exhausts its supply of gas and dust needed to create new stars. The brilliant spiral arms that currently define our galaxy's appearance will slowly fade as massive stars die off. Eventually, our galaxy will be dominated by small, long-lived red dwarf stars that burn their fuel so slowly they can shine for trillions of years. The merger with Andromeda will transform our familiar disk-shaped galaxy into a more spherical elliptical galaxy with completely different internal structure and dynamics. Star colors will shift dramatically as hot blue and white stars disappear, leaving behind a galaxy illuminated primarily by the dim red glow of small stars and the fading white light of stellar remnants. Planets will become increasingly rare as stellar evolution destroys existing planetary systems and new star formation becomes too infrequent to create many new ones. Any civilizations that survive these cosmic changes will inhabit a galaxy where stars are separated by much greater distances and new stellar neighbors are almost never born. The cosmic home that has nurtured our solar system for billions of years will slowly transform into an alien galactic environment, unlike anything we could recognize today. Every 140 million years, our solar system's passage through galactic spiral arms exposes Earth to dramatically increased levels of cosmic radiation. These high-energy particles streaming from young massive stars and supernova explosions penetrate Earth's atmosphere in much greater numbers during spiral arm transits. The radiation increase isn't immediately lethal, but it creates subtle evolutionary pressure on all life forms. Cosmic rays can damage DNA in living cells, leading to increased mutation rates across entire ecosystems. Most mutations are harmful or neutral, but some provide advantages that help organisms adapt to changing environmental conditions. The timing of these cosmic radiation pulses roughly coincides with several major evolutionary transitions in Earth's fossil record. Periods of increased species turnover and rapid evolutionary change sometimes align with when our solar system should have been passing through spiral arms. Enhanced cosmic radiation might also affect Earth's climate by influencing atmospheric chemistry and cloud formation patterns. Changes in cloud cover can alter global temperature patterns and precipitation cycles. The combination of direct radiation effects on organisms and indirect climate influences creates complex evolutionary pressures that shape the development of life over cosmic time scales. Our periodic journeys through the galaxy's most active stellar regions might act as cosmic pacemakers that accelerate evolutionary change and biological innovation on Earth. What happens to Earth's protection from cosmic radiation when our solar system encounters regions of denser interstellar material? Our Sun creates a magnetic bubble called the heliosphere that normally extends far beyond Pluto's orbit. acting like a cosmic windshield that deflects harmful radiation from reaching the inner solar system. When we pass through denser interstellar clouds, the increased external pressure compresses this protective bubble dramatically. A compressed heliosphere allows more galactic cosmic rays to penetrate closer to Earth. These high-energy particles can reach our planet's upper atmosphere in greater numbers, where they interact with atmospheric gases. The increased cosmic ray bombardment can trigger changes in atmospheric chemistry that affect climate patterns. Cosmic rays help create clouds by providing particles that water vapor can condense around. More cosmic rays typically mean more cloud formation, which can lead to global cooling as clouds reflect sunlight back into space. This mechanism might explain some of the climate variations Earth has experienced throughout its history. The heliosphere compression effects can last for thousands of years as we slowly transit through dense interstellar regions, creating prolonged periods of altered cosmic ray exposure and potential climate influence. Our solar system's magnetic shield periodically shrinks when we encounter cosmic traffic jams, potentially affecting Earth's climate through subtle but persistent changes in atmospheric physics. When massive stars explode as supernovas within a few hundred light-years of our solar system, Earth receives devastating doses of high-energy gamma rays and X-rays. These stellar death explosions release more energy in seconds than our Sun will produce over its entire 10 billion years lifetime, and nearby events can temporarily overwhelm Earth's natural radiation defenses. The high-energy radiation doesn't directly harm life on Earth's surface, but attacks our planet's protective ozone layer in the upper atmosphere. Gamma rays and X-rays break apart ozone molecules, creating holes in the atmospheric shield that normally blocks harmful ultraviolet radiation from reaching the surface. With a damaged ozone layer, deadly solar ultraviolet light penetrates to Earth's surface in much higher doses. This UV radiation can kill marine plankton, damage plant life, and increase cancer rates in surface-dwelling organisms. Geological evidence suggests that at least 2 nearby supernova explosions have occurred within the past 10 million years, based on radioactive isotopes found in ocean sediments and polar ice cores. Some mass extinction events in Earth's fossil record might correlate with supernova explosions that temporarily removed our planet's UV protection and disrupted food webs. When massive stars die violently near our cosmic neighborhood, the radiation storms they create can temporarily strip away Earth's atmospheric defenses and expose all surface life to lethal solar radiation. Earth's history of ice ages might be connected to our solar system's regular passages through the galaxy's main disk every 33 million years. During these galactic plane crossings, our solar system encounters higher densities of cosmic dust that can partially block sunlight from reaching Earth's surface. The dust acts like a cosmic sunshade that reduces the amount of solar energy Earth receives. Even a small reduction in solar heating can trigger ice age conditions if it persists for thousands of years. Ice reflects sunlight back into space, creating a feedback loop that amplifies the cooling effect. The correlation between our galactic oscillations and ice age timing isn't perfect, since many other factors influence Earth's climate. Volcanic eruptions, changes in ocean circulation, and variations in Earth's orbit all play important roles. But some researchers have identified suspicious patterns in the geological record that suggest galactic dust encounters might provide the initial trigger for some ice age periods. The mechanism would work gradually over thousands of years, making it difficult to distinguish from other long-term climate drivers. our regular journeys through the galaxy's dusty central disk might occasionally dim the sun just enough to tip Earth's climate system into ice age conditions. As our solar system travels through different regions of galactic space, we encounter varying interstellar magnetic fields that can distort and weaken Earth's protective magnetic bubble. Earth's magnetosphere, the magnetic field surrounding our planet, normally deflects most harmful cosmic radiation away from our atmosphere. But this protection isn't constant as we move through different cosmic environments. When our solar system encounters regions with strong interstellar magnetic fields oriented opposite to Earth's field, the conflicting magnetic forces can create gaps in our planetary magnetic shield. These magnetic interactions can trigger spectacular aurora displays as charged particles penetrate deeper into Earth's atmosphere than usual. But they can also allow more cosmic radiation to reach our planet's surface. Changes in the interstellar magnetic environment might influence the frequency and intensity of geomagnetic storms that can disrupt satellite communications and electrical power grids. Over longer time periods, sustained changes in our cosmic magnetic environment could affect atmospheric chemistry and climate patterns through altered cosmic ray exposure. The strength and orientation of interstellar magnetic fields varies dramatically throughout our galactic orbit, creating a constantly changing electromagnetic environment around Earth. Our planet's magnetic protection constantly adapts to invisible cosmic force fields that shift and change as we journey through different galactic neighborhoods. Our solar system's vertical oscillations through the galaxy create periodic increases in comet bombardment that have profoundly influenced the evolution of life on Earth. Every 33 million years, galactic tidal forces peak during our closest approaches to the galactic plane, gravitationally disturbing the distant Oort cloud and sending showers of comets toward the inner solar system. These cosmic snowballs carry both the ingredients for life and the potential for mass destruction. Comets contain water, organic compounds, and other materials essential for life. Early in Earth's history, comet impacts may have delivered much of our planet's water and the complex carbon molecules that became the building blocks of biology. But large comet impacts can also cause mass extinctions by triggering global climate changes, massive volcanic eruptions, or direct destruction through impact effects. The geological record shows evidence for periodic increases in impact cratering that roughly correlates with our galactic oscillation cycle, suggesting that cosmic timing influences terrestrial bombardment rates. Some extinction events appear to coincide with predicted peaks in comet delivery, while other impact episodes seem to have stimulated evolutionary innovation by opening new ecological niches. Our galactic dance periodically shakes loose armies of comets that act as both cosmic delivery trucks bringing life's raw materials and cosmic bullets threatening existing life forms. Microscopic amounts of interstellar material constantly infiltrate Earth's atmosphere as our solar system moves through different cosmic environments. These cosmic contaminants include exotic molecules, unusual isotopes, and chemical compounds that don't occur naturally on Earth but form in the cold depths of space or around dying stars. The quantities are incredibly small, but they accumulate over millions of years. Interstellar dust particles that penetrate our solar system's magnetic defenses eventually settle into Earth's upper atmosphere, where they participate in complex chemical reactions with atmospheric gases. Some interstellar molecules contain heavy isotopes, forms of common elements with extra neutrons. that create distinctive chemical signatures in atmospheric measurements. These alien chemical inputs might influence atmospheric chemistry in subtle ways that affect ozone formation, cloud nucleation, and other processes that influence Earth's climate system. The chemical composition of interstellar material varies dramatically depending on which cosmic environments we're passing through, creating constantly changing inputs to Earth's atmospheric chemistry. Scientists can detect these interstellar chemical signatures in ice cores, ocean sediments, and atmospheric measurements, providing a record of our solar system's journey through different galactic neighborhoods. Earth's atmosphere continuously receives tiny doses of alien chemistry from deep space that slowly modify our planet's chemical balance over cosmic time scales. Our solar system's 33 million-year vertical oscillation through the galactic disk creates subtle but persistent climate influences on Earth through changing cosmic radiation exposure. As we rise above and sink below the galaxy's central plane, we encounter different cosmic radiation environments that affect atmospheric chemistry and cloud formation. Near the galactic disk, higher cosmic ray intensities increase cloud formation, which can lead to global cooling as more sunlight gets reflected back into space. During our excursions above and below the galactic plane, reduced cosmic ray exposure decreases cloud formation, potentially allowing more solar heating to reach Earth's surface. The climate effects are small compared to other natural climate variations, but they persist for millions of years at a time, creating subtle background climate rhythms throughout Earth's history. Some researchers have identified weak correlations between our galactic oscillations and long-term climate trends in the geological record, though the connections remain controversial. The mechanism works through cosmic ray influences on atmospheric chemistry rather than direct heating or cooling effects, making the climate signal difficult to distinguish from other long-term climate drivers. Our vertical dance through galactic space creates a gentle cosmic metronome that may help pace some of Earth's longest climate cycles. Changing cosmic environments during our galactic journey don't just threaten life on Earth. They actually stimulate biological diversity and evolutionary innovation. When our solar system encounters new interstellar environments, cosmic radiation levels, or gravitational disturbances, these changes create evolutionary pressure that drives biological adaptation and speciation. Species that can adapt to changing environmental conditions survive and diversify, while those that cannot adapt become extinct. The net result is often an increase in biological diversity as surviving lineages evolve into new ecological niches opened up by environmental changes and extinctions. Cosmic environmental changes happen gradually over thousands to millions of years, giving life time to adapt, rather than simply wiping out everything at once. The fossil record shows that some of Earth's greatest bursts of evolutionary innovation occurred during periods that coincide with major cosmic environmental transitions. These episodes of punctuated evolution might represent life's response to changing cosmic conditions as our solar system moves through different galactic environments. Even mass extinction events, while devastating in the short term, often lead to explosive evolutionary radiation as surviving species diversify to fill empty ecological roles. Our journey through an ever-changing cosmic landscape acts like a biological catalyst that periodically accelerates evolution and increases the complexity of life on Earth. Over the next 100 million years, our solar system's continued galactic journey will expose Earth to cosmic environmental changes that will challenge the long-term survival of complex life. Our upcoming passage through the Perseus spiral arm will increase cosmic radiation exposure for roughly 10 million years, potentially affecting atmospheric chemistry in global climate patterns. Future encounters with dense interstellar clouds will compress our heliosphere and allow more galactic cosmic rays to penetrate Earth's atmosphere. Predicted close passages of nearby stars will gravitationally disturb our outer solar system, potentially increasing comet bombardment rates and impact risks for Earth. The eventual collision with the Andromeda Galaxy will completely reshape our cosmic environment and create unpredictable gravitational chaos throughout our galactic neighborhood. These future cosmic challenges will test life's ability to adapt to changing environmental conditions over time scales much longer than any individual species' typical lifetime. However, life on Earth has already demonstrated remarkable resilience by surviving multiple cosmic environmental changes throughout our planet's 4 billion years biological history. The key to long-term survival may be maintaining high biological diversity so that some lineages can adapt to whatever cosmic changes the future brings. Earth's biological future depends on life's ability to remain flexible and adaptable as our cosmic environment continues to evolve over astronomical time scales. As our solar system speed through galactic space changes over cosmic time, these velocity variations alter how interstellar material interacts with our protective magnetic environment. Higher speeds through interstellar medium create stronger cosmic headwinds that compress our heliosphere more severely and change the geometry of our magnetic shielding. Lower speeds allow our heliosphere to expand farther from the Sun, potentially providing better protection from galactic cosmic radiation. These speed-dependent effects create complex feedback relationships between our motion through space and Earth's cosmic radiation environment. Changes in our galactic orbital velocity also affect how quickly we transit through different interstellar environments, altering the duration of exposure to various cosmic conditions. Faster transits mean shorter exposure to dangerous cosmic neighborhoods, but also shorter exposure to beneficial cosmic environments that might provide enhanced protection. Here, the relationship between orbital speed and cosmic environmental exposure creates a delicate balance that has helped maintain Earth's habitability throughout our planet's history. Future changes in our galactic orbital characteristics could shift this balance in ways that either enhance or reduce Earth's protection from cosmic hazards. The speed of our journey through space acts like a cosmic thermostat that helps regulate how intensely galactic environmental changes affect Earth's climate and biological systems. Over billions of years, the cumulative effects of galactic environmental changes will create the ultimate test of life's ability to survive and thrive in an ever-changing cosmic environment. As our galaxy evolves, star formation declines, and cosmic conditions shift dramatically, Earth's biological systems will face environmental challenges unlike anything they've experienced before. The key to long-term survival lies not in avoiding cosmic changes, but in maintaining the evolutionary flexibility to adapt to whatever changes occur. Life's greatest advantage is its diversity. The vast array of different species, genetic combinations, and biological strategies that exist simultaneously on our planet. This biological diversity acts like an insurance policy against cosmic environmental changes. When conditions change, some species will be better adapted to the new environment than others. The survivors will inherit the Earth and diversify to fill ecological roles left empty by extinct species, creating new forms of life adapted to the changed cosmic conditions. This process of cosmic adaptation has been happening throughout Earth's history and will continue as long as our planet can support liquid water and complex chemistry. The ultimate measure of biological success won't be avoiding change, but embracing it as an opportunity for continued evolution and adaptation. Life's cosmic future depends not on finding a perfectly stable environment, but on maintaining the evolutionary creativity to adapt to whatever cosmic changes the universe provides.